it?
Yes. If you face any issue with your audio, I think you can switch off your video.
Yeah,
I
yeah,
think
I
then
should
I
because
mean, you don't face any network issues, I guess. Yeah.
I do not have broadband connection, so I rather like this. Okay, so I will continue. Okay, so the very first thing that usually when we see or look at the night sky, and that comes to our mind is what are those twinkling objects? Although I named my talk after twinkling stars, but I hope it is very clear to most of the audience that stars actually do not twinkle, but they appear to be twinkle because of the atmospheric interference of our Earth. So the very first question that should come to our mind is how do these stars fo- form or come to existence in the first place, and why are they even shining? Why so bright in the night sky? And then another slightly scientific question is, as we all know, that universe has abundance of hydrogen and helium, but still on Earth we already know that there have been at least 110 naturally occurring elements already discovered, plus 10 more artificially generated elements are there. But where do they come from? The entire universe has hydrogen and helium in abundance. Where are these heavier elements coming from? Then the next question that should come to our mind is, there are stars which we can clearly see in the night sky. There are planets in our solar. Obviously, there are several planets which we cannot see directly through our naked eyes, but there are several planets with mostly all of the stars. So, how do these planets come into existence? First the stars, then the planets, and lastly, these stars keep on twinkling in our night sky. And but what actually happens when they stop twinkling, or they actually like become old? As humans we also grow old, so what happens to the stars when they grow old? How do they die, and what eventually becomes of them? So we usually have these telltale stories in our culture that when people die they become a star, but the question is, what do stars become when they die? So I hope this will be clear by the end of today's talk. But die. Okay, so okay. The very first point to discuss is, there is some technical issue. I guess my slides are not clearly working. Just a minute. They
Yeah,
should.
it's okay. It's okay.
Yeah, this is the problem with. Okay, so the very first thing that the answer to the very first question in the previous slide was what are stars, how do they form, and how do they shine. But let us quickly summarize what these stars are actually in respect to the entire universe. So what significance do they hold? So stars are basically the cosmic engines of the entire universe. They drive the entire evolution of our universe. So as we know, they generate a lot of energy, and some part of that energy we observe as in the form of light. So these stars not only just produce this energy, but they are also helpful in driving so many phenomena throughout the entire, that we can call them the basic engines of the universe. Just like the car engine that drives the car from one place to another, these stars are the engines that will drive the universe from its beginning up till its current stage, and eventually to its end also. Then these stars, as they are engines, they are producing something. So apart from the light, they are also producing some newer exotic material, which we call the heavy elements that we find naturally occurring on our Earth also. So the answer to previous question was, how, from where do these heavier elements come? So these actually comes from the stars themselves. Then the next is, the next question was, how do planets form? Okay. planets actually form from the remnant of from what the stars form. I will actually give a glimpse of each and everything in the coming slides. But just to quickly answer or summarize the previous points, so stars do not only exist alone, they also trigger the formation of planets as well. And then the last question, what happens when they die? So basically, as I mentioned, they make a very drastic exit from their existence and leave some very interesting objects in their wake when they die. And what are those possible objects? We will quickly see in the following slides. Okay. I hope these slides work correctly. So now, like if most of you have observed Orion constellation, I guess most of you must have observed. So if you see the two diagonally opposite stars appear to be completely different in color as well as in size. So basically, the stars that we usually see in the night sky, they may appear to be all the same, but if you try to observe them through telescopes or some like combination of optics, you will observe that not all stars have the same color and are also not of the same sizes. So the stars in the universe have different characteristics. So they can be of different sizes. And by size, I mean if the star is bigger, obviously it will be more heavy or more massive. If it is smaller, it will have less mass and its size will be obviously small. Then the color of the stars are not always the white that we usually see through our Earth's atmosphere, but these stars exist in several different shades. So, starting with the mass, for example, as you may see, the very tiny spot, I guess that is our sun, that we see as a huge star and the closest and the only star that is in the proximity of our planet, not even visible on this scale. So, sun is so tiny as compared to the largest stars that can exist in the universe. There, this is Regal Star. Then there is 119 Tauri and Antares. So all these stars actually exist in the universe, but since we are seeing them at such a distant point, all they appear to be of the same size and same color. But actually, in the universe, stars come in a wide range of masses. So like from one solar mass, you can get a star that is about 100 solar masses also. That means you can fit 100 sun into that star, and that those stars also exist in the nature. And the next is the variation in color. So usually they all appear like this or this, the white light stars, but actually their color also differ depending on the size of the star. For example, this is the Sirius star, and this is Betelgeuse. That is one of the stars that appear larger and orangish in the Orion constellation if you observe it very carefully. So you can see there are different shades of color for each and every star. This is just a small sample of the entire color collection of these stars. So if you observe these stars using very good magnification of telescopes, you will actually see the different colors of these stars. So the colors of the stars are not limited to just white, but we can have different colors. And these colors actually come from what? Their like size, and to be very precise, the temperature of that particular star. The surface temperature of a different star will give you some different color, and we will see it as different. For example, our sun's temperature, surface temperature is around 5000 Kelvin. So that's why it appears to us yellowish orange or orangish yellow, whatever you choose to call. But if temperature of a star surface is very high, for example, of the order of, okay, then again, this slide, just let me quickly fix this. Just a minute. Okay, go, and All right. So here. So as you see, I have all the three basic properties of different stars. So as the mass increases, here the mass is written in the terms of mass of the sun, that is solar mass. So for stars that are slightly lightweight as compared to our sun, they will appear reddish as compared to our sun, and their surface temperature is like two-thirds of the surface temperature of our sun, around 3,500 Kelvin. But as you arrive at stars which mass as our sun, the color of those stars will appear to be yellow that we see for our sun itself, and the temperature for their surface will vary between these two, this range. And as you keep on increasing mass, the color of the star will eventually change depending on the temperature of its surface. For example, if you have a very massive star that is greater than 16 solar masses, then the color of that star will appear to be more bluish rather than white, and the surface temperature of those stars will be approximately more than 30,000 kelvins. So these three basic properties of the stars can be found in the entire universe when you are observing different stars from different regions of the sky. Then the next is, like we have discussed, that there are different types of stars, different masses, different colors, different temperatures. Now the question is, how do these different types of stars actually form? Is it that one type of star is formed like independently in a like isolated region, or the group of stars form at once in the universe, or there is something else happening? So obviously, as we all know, that the entire universe is filled with hydrogen and helium. Since the Big Bang, the most of abundant elements till today in the entire universe are hydrogen and helium. So it is like very intuitive to guess that the star should be made up of mostly these two elements only, because since there are only trace amounts of other heavier elements, so stars cannot be completely made up of all the heavier elements or some different heavier elements. Mostly they will be made up of this hydrogen and helium. But to make this star, what do we actually require? So let us like break down the recipe of star formation. So the very first thing, the very first key ingredient that you require to for the star to form is this hydrogen and helium gas. Since it is very abundant throughout the entire universe, you can find it like in the most of the region of the observable universe, that there are some like dense cloud material like molecular hydrogen and molecular helium gases. And in those regions, you can expect that the stars are forming. But it's not that if you have the material, you can just create the star. Because obviously, if you, any one of you have worked in the kitchen, just having the ingredients to make star, you need some driving force behind it, something to get something from those ingredients. So we have the first ingredient, that is the material itself, and it comes in the form of interstellar medium. So because it exists in between the different stars that have already formed in the past, so we call it the interstellar medium. Then the next, like to define what this interstellar medium is made up of, again I had this glitch. Okay, let us just skip. So basically, this interstellar medium is made up of cold gases that are so cold that they have formed from atomic state, they have transformed into the molecular state. So two hydrogen atoms have combined to form the molecular hydrogen gas H2. Similar for the helium, that it has cooled down to clump together and form some cloud. The water vapor clouds in Earth's atmosphere, similar types of clouds exist, different stars, different stellar systems in the entire universe. So basically, the interstellar medium is made up of such cold gases that we require to give birth to stars. Then the second thing, the driving force that I was giving an example for the actual cooking that we do, the driving force, there, the driving force is us, here the driving force is the gravity, the ubiquitous gravity that exists everywhere, that is omnipresent in the entire universe. So that gravity plays the defining role or the deciding role in the formation of these star systems. As you can see, here is a small animation. I hope it is at least clear enough to see some tiny dots of these specks. Those are actually the stars that are like coming into existence in these molecular clouds. And again, so, like I'd like to reinstate that to both the key ingredients, just the existence of material and gravity will not result in the formation of stars. You require a very precise balance of what mass you have and what the condition exists for that particular given mass, then only you can have stellar formation. It's not like we can form stars in our laboratory on the Earth also, because we can produce obviously hydrogen and helium. We have abundance of that. We also have gravity that is present on the Earth itself, but we cannot form stars because this formation actually requires a very precise balance of each and every ingredient. So I guess both the key ingredients for these stars, star formation, are very clear to you. Then again, mentioned that you require some precise value of mass, and if you invoke us like little bit of physics, so for cloud that is not dissipating away, or like all the particles of that cloud are not going farther away from its center, we call such type of system as a gravitationally bound system, where gravity tries to keep each and every particle together within that cloud. And for that condition, we apply some theorems. Usually we call it the virial theorem. From there, we get a minimum required mass that is called the Jeans mass. This much mass you must have at the beginning to get some star formation from the dense interstellar material cloud in the universe. If you fail to acquire this much mass, so the stars will not be formed in such cloud. That is why we do not see stars in our entire sky at each and every point, because obviously there exists some ISM in the like in all the directions, but not but mass of not all those clouds meet this criteria, and hence we do not have like stars in entire the sky or the universe. Otherwise, it would appear to be like infinitely many stars in the night sky also. So then the night skies would be filled of uh, like white, yellow, and blue lights from all the stars if each and every cloud of that gas converts into stars. So this plays a very important role in the star formation. And then, okay, so once we have the ingredients, the very first thing we have interstellar material cloud, then we have the gravity, then if fortunate enough, if we are fortunate enough, we get accumulate Jeans mass. What happens actually? So here is a quick short video that will show you that how these star formation take place. So this, when we start, this is a gas cloud which is gradually like mixing in itself, and it is giving rise to some local dense regions, which results in the formation of these tiny specks, which will eventually come into existence as the stars that we observe. So just to quickly, okay, just a minute. Okay, this the video. This is not in full screen, I guess. Hmm. Yeah. So we start with a chunk of cloud, and you can see the time evolution. This is in millions of years. 1 million is 10 to the power 6 years actually. So it takes so much of time for a gas cloud to intermix in itself and the gravity to play its significant role to create regions of local dense material which eventually start collapsing on itself and leading to the formation of stars. So these tiny specks, these tiny white specks that you see in this simulation are actually the baby stars, or what we call them in like scientific language are the protostars. Actually, these are not technically complete stars yet, but they eventually further evolve with time, and then they become the fully fledged stars that we see in our sky. And like since these are completely enveloped or covered in this dense material, these initial stages of star formation are not actually visible through uh, like any type of telescope so that we can observe them. And that is why this is just a simulation of how stars are formed. You can just observe such kind of stages, very early stages of the initial star formation through radio telescopes and all, which will not give you the exact image that we see. So hence this simulation helps us to visualize that how these stars actually form. So okay, I'll skip this portion, the external triggering mechanism. That I will come to it by the end of my talk. So now the second stage that you already saw in the previous animation, that you see those tiny white specks, those are the protostars, or what we call them, a protostar. So protostar is basically what? A local dense region of that material which is like getting compressed due to the gravity, and at the center of that local region there will be immense material collapsing on itself, producing very high and large temperatures, and that is why it starts to glow, and this is what forms this protostar. For example, you can pay attention to this animation in this screen. So this is a local region of material. So after some time, what happens is it starts to collapse on itself. This is the dense region, and at the center the gravity is actually pulling the entire material to the geometric center of this region, and the temperature starts to increase and gives rise to the protostar. And as it starts to glow, most of the material surrounding it is actually thrown away. So it does not just continuously keeps on taking the material all the way. It at some point it just stops taking the outside material onto itself. Then the third state, it is again a very scientific kind of stage, but I will just give you a glimpse of it. This is called the T Tauri phase. This is again the similar the last animation. So if you will observe carefully, once these tiny little specks are formed, which are the protostars, they also start spilling some orange material in two directions. Just carefully observe these. Okay, so here you will see these jets kind of thing. So they are spilling actually the extra material that is falling onto them like this. So this phase is actually called the T Tauri phase. It's like similar to some like young stars that they also show such kind of phenomena. So that is why this is named after them, the T Tauri stars. So this is the phase where these protostars actually spills the extra material that is coming onto them. So they just throw it away in forms of two like oppositely directional jets. Then we can continue to next stage. Once each and everything has settled down, the protostar has, okay, again, the content of the slide is missing. Okay, so once the entire protostar has, huh, sorry for these glitches. Okay, once the protostar has ejected extra material through these jets, in the surrounding, it will eventually come to a equilibrium state or a stable state, and that is what we call the actual stars. The stars that we today see has already gone through all these phases, and now they are in this stable form, which is called the main sequence stage of their life. Stage 4 is actually the longest existing phase in the entire life of a star. So all the stars that not all, mostly like all of the stars that we are observing or we see in the night sky are actually in their main sequence stage. Most of them, okay, some of them have actually evolved and had gone through all this stage and they have now become giants and all. But most of the stars that we observe are in their main sequence stage. And like, how do we distinguish between these different stages? That when do we call a star a protostar, a T Tauri phase, or a main sequence stage? So, in the main sequence stage, the most defining characteristic of any star should be that in its core, the hydrogen that from which it was formed initially is undergoing the hydrogen fusion reaction, which creates helium and a lot of energy that we see in the form of light coming from those stars. So, all those stars in which at their center the hydrogen fusion is going on are like classified as the main sequence star. So, this is the longest uh, like phase of a star, and this is basically mostly the most stable state of a star. During this state, no extra material is getting onto the star, nothing is getting out of the star, everything is there. Only the uh, like dynamics that is happening, only the changes that are happening are inside the star, and that even in the core of the star. So the temperature of the cores of such stars actually exceeds 10 million Kelvin. 1 million is 10 to the power 6. So we are talking about the temperatures of the order of 10 to the power 7 Kelvin. And required to bring two hydrogen atoms forcibly close to each other and form the helium atom and also emit some energy. That emitted energy is what we actually see as in the form of light coming from these stars. So this is the longest running phase. Then there is this another slightly scientific aspect of these stars. So as I mentioned, just quickly summarize this. As I mentioned in the beginning, that stars come in all different flavors. They can be of any mass, they can be of they can be of like any surface temperature. But is it actually so that we can expect any combination, any random combination of star? So can I expect a star which has mass that is equals to sun's mass, but it has blue color and its temperature is 1000 Kelvin? So can we like expect the nature to prepare any random combination of stars? So if that is true, we will observe something like this, that if you try to plot the properties or the stars with respect to some specific prop, some random scattered plot, that all possible combinations are there. But what turns out that nature has a pattern. So it is not that you can expect any random combination of stars, but we'll see that low mass stars that are comparable to our sun or even lighter than our sun will always be having colors that are like within red and yellow, and their mass and their surface temperatures will be like more or like less than 6000 Kelvin. Then if you take slightly heavier stars that are few solar masses 1 to 10, you will see that they will have more prominent light in the range of like light blue and still yellow, and their surface temperatures will be of moderate range up to few thousands of Kelvin, few like tens of thousands of Kelvin. But for heavier stars that are made up of like a very large amount of hydrogen and helium, they will always have very high surface temperature of the order of 30 to 35 thousand kelvins, and their color will always be the blue color of your visible spectrum will be pure. So you will see that nature has some specific way of making these stars. And when you plot all the information about such observed stars, you see a diagram like this. Type of distribution of stars in the universe is represented by a diagram which is known as the HR diagram, which stands for two scientists who independently discovered this fact about the universe, and the name of those scientists were Hertz and I guess Hertz and Russell Spring, I guess. If anybody else knows the correct name, they may like unmute themselves, because I'm okay. Hertzsprung and yeah, Russell. Okay, Hertzsprung and Russell. So they independently discovered about this fact about the yeah. Okay, yeah, I got the name in the next slide. So it is, that is why it is called the HR diagram. Okay, so this is more like a more scientific type of thing. So these HR diagrams helps in basically the research studies and or more detailed studies about the star. But still, it is fascinating to know that nature also works in a specific pattern, not just random. Now, okay, so before moving on to the next stage, I will just take the help of this HR diagram. And okay, I should have mentioned it before. Okay, so like in this diagram, okay, in the next diagram, it will be more clear. Huh. Okay, so when you see this type of pattern for a very large number of observed stars, so this pattern can be divided into different regions. For example, the lower, like bottom right corner is generally called the low main sequence. This region where our sun sets in this diagram is called the main sequence, because our sun is also in its youth and it will spend like approximately 4.5 billion more years on this at this place in this graph, and then eventually it will evolve into a white dwarf. It will come downwards. That is a topic for the next slides. And then this region where the heavy or the massive stars exist are called the is called the upper main sequence stars. So the evolution of these three regions, or these three broadly classified stars, is completely different. So just quickly tell you that how these different types of stars actually evolve. Again, I have to quickly do this. Hmm. So the stars that were there at the bottom right corner, that means this region of that HR diagram, actually are called the low main sequence stars, and they are classified with the lower mass. And obviously the light that is being emitted from these stars is coming from the fusion of hydrogen inside their core. But once entire hydrogen in their core is depleted, all the hydrogen has been used up in the reactions and everything has been converted to helium, what actually happens is there is no stability left in these stars. So the gravity will now start to push that star further, and this will trigger some unstable state or unstable state in these stars, which will actually result in not a compressed star, but because of some other dynamics going on these stars, it results in the formation of a giant star. So this giant star phase is actually when the star that was originally of some size is larger than that size after its entire hydrogen has been used up. So how these actually go is slightly scientific, so I'll just skip it for now. But just understand, for low mass stars, what actually happens is as the hydrogen depletes, the gravity tries to push it, and as it starts to push, the temperature actually increases. And as the temperature will increase, the helium that is left in place of hydrogen starts to fuse now. And the hydrogen that was just at the boundaries of such stars, which was not used up in the core, because you have different regions in the stars, that fusion just take place in the core. The hydrogen that exists outside the core do not get used up. So when the gravity compresses it, the temperature of that outer hydrogen also starts to increase and it starts to fuse, which results in expansion. So you observe what the star has now grown larger than its original size, and this phase is called the giant phase. Similarly, in this phase, there exists two different regimes depending on the mass of the star. So if the star is very low mass star, so you will get different type of giant. If the mass of the star is slightly higher, you will get a different type of giant. And characteristically, the color of these phases of a dying star is usually red. So that's why these are also called the red giant stars. Okay, and Betelgeuse is right now in a giant phase, and that is why it also appears red, which is in the Orion constellation that I was talking about earlier. So it is not a main sequence star, but it has left the main sequence and it is actually dying. It will eventually die and become something. And what are the possible options that I will quickly cover here? I have 15 more minutes, I guess. Okay. Now, the upper main sequence stars that were at the top left corner, this region. What happens to them is again a very scientific kind of a journey. As you can see, they this, and that, but eventually they also becomes very like low mass stars become red giant. The heavy mass stars actually becomes red supergiant, and Betelgeuse is a red supergiant. Actually, technically, it is in the giant phase, but it is a supergiant right now. So again, what happens is in heavy mass stars, the hydrogen depletes, then the gravity pushes it and tries to. Then the hydrogen outside starts to fuse, helium inside starts to fuse. Then again, hydrogen and helium are depleted. Then gravity again starts to compress. Then after helium fusion, carbon is formed. Then carbon starts to fuse, so on and so on. And you get something like this. Or a heavy star, when it starts to die, you see different layers or an onion type of a thing in a star. Heavier elements at its core keeps on fusing and fusing. The lighter elements are fusing in their outer shells, and you get something like this. And this continues. You have a complete iron core. That means all the previously created elements have now fused, and we are at the iron at its core. Now, what happens is after the iron is formed, no further compression can result in for its further fusion, because iron cannot be fused efficiently to produce energy. It actually takes up energy to fuse, and that is why it is not favored further continue to fuse and form the heavier elements. So at least clear up till now that we started with stars that had hydrogen and helium in them, but for massive stars, we get all these heavier elements formed while they are dying. They are actually going to get away from their existence, but even while they are dying, they are doing some good for mankind, that they are forming the heavier elements. So up till iron, all these previous elements are actually formed in the core of a dying star. So that at least answers the second or third, yeah, second question from my first slide. And for like comparison, okay, so the core of this uh, iron region in the stars is approximately of the size of the Earth. But then, as I mentioned, that no further fusion takes place, so this formation or the synthesis of heavier elements completely stops at the formation of iron. You cannot expect further heavier elements beyond iron to form in a dying star. But then again, the question remains: then how do further heavier elements come into existence if even the most massive stars in the universe are not forming them? So we will come to that in a bit. That what happens when everything in the core has depleted and you are just left with the iron in its core. core. So then comes the dramatic event that most of you must have heard about, that is called the supernova, which is actually the death of a massive star. A massive star which is continuing to fuse heavier and heavier elements, eventually settles down with the formation of iron in its core. But no amount of compression can further fuse this iron to produce further energy. So what happens is that gravity keeps on compressing it, but eventually what happens is there is a like a violent kind of explosion, which is known as the supernova. And basically the core of that star, which was completely made up of iron by the do what? Since it is very dense, and when the gravity was pushing all the outer layers of like slightly lighter elements before the iron, it pushes all those layers onto the core. But since core is made up of iron and it cannot further squeeze, all those layers actually go and strike that iron core and bounces off back with a huge explosion type of thing, which we observe or which we call as the supernova. And as a result of this, what happens is the entire elements before that iron and some of the iron gets dissipated away in the surroundings of that dying star, as you can see in this animation as well. So this is how a supernova actually looks like. It can actually outbright an entire galaxy in which it is happening. It is such an enormous energetic event, and one of the most energetic events that happens in our universe. So it releases a large amount of energy because of that collision of the outer layers with their dense iron core. Then again, these can be classified into two types, type 1 and type 2. The one that I'm talking about is the type 2 supernova. Type 1 supernova happens in white dwarfs. That is a different thing. If I get the time, I can discuss about it. And now the point is, what is the basically the takeaway from this? All of this story that a very large massive star starts from hydrogen helium, it keeps on synthesizing heavier materials, at the end it forms iron, and then it like ends up with a supernova. So all that heavier elements before that iron was formed are actually distributed in the universe through this supernova, and that's how we actually have heavier elements in on our earth and all other planets, because it actually came from the death of some massive stars back in the past, sometime, somewhere in the universe. So this is the significance of these stars, that supernova remnants enrich the interstellar space with heavier elements and planetary nebula. So from these dissipated material, when the planets will be formed, somehow due to some phenomena, those planets will actually have all these elements in them. Then, okay, so now, like everything has happened. Upper main sequence star has evolved. It has exited through a supernova now, and it has thrown away all the heavier elements before iron in the interstellar medium. But what happens to the core, that iron core? What becomes of it? Will it exist? Will it be destroyed, or will it become something else? So this is the last stage of a star that it will ever have, and then it will cease to be called a star. So one thing is left after a star undergoes. So, and that remaining thing is actually called the core remnant, obviously, as the literal meaning, the remnant of the core of the original star. So, I hope this slide works. Okay, it is not working. Work. What happened? Just a second. Okay. So What could be the possible outcomes of this core remnant? Now, the very first possibility, if the star that we were talking about had a mass uh, like of around 8 to 10 solar masses, then after all the different layers have been fused and the other elements have been formed, if the mass of that iron core or the core, just leave it iron because then I will be technically incorrect, because for white dwarfs the core is usually of helium or carbon. So the if the unfused core on collapse happen is a mass which is slightly 1 by 3 by 2 of the sun solar mass or mass of the sun, then that remnant will be a white dwarf. I hope some of you at least know what dwarfs are. So these are just completely bluish white light emitting very dense objects in the universe. So a star whose core, not the original star, whose core, the unfused core, was approximately 3 by 2 times of the mass of the sun, will eventually become a white dwarf. So for these like to get these conditions, we initially require a star that started with an actual mass of around 6 to 7 to 8 solar masses. And these are very dense, very small, of the order of few thousands of kilometer radius or the complete diameter of these stars. And these are very, very, very hot, and hence they emit light in blue or white region. And similar to the supernova, the outer layers of these stars are actually thrown away. Then the next is, if the mass of that core that was left unfused is somewhere between 1.4 to 3 solar masses, then that star, that remnant will actually become a neutron star. Not the white dwarf, but a neutron star. And what is the characteristic of such neutron stars is that the core has now become enriched of neutrons. Some of you know what neutrons are. Neutrons are the constituents of the nucleus of an atom, and these neutron stars are actually formed from the remnant of original stars that had mass greater than 8 solar masses. And uh, like during the journey of their life, all of that mass was fused up, and the core that remained unfused was of iron, and it weighed somewhere between 1.4 to 3 solar masses. And after the supernova happened, they found it, what they leave behind is a neutron star, that is a neutron rich star. Like most dense objects that are formed in the entire universe, and these are more very, very, very compact, hence they are most dense. The size of neutron stars typically ranges between 10 to 20 kilometers only, like the size of a city only. And these are also like very fastly spinning objects in the universe. Most fastly spinning objects in the universe are the neutron stars. Uh, And along with that, these are the heavily magnetized objects that exist in the universe. So if some of you have heard of magnetars, which have the magnetic field of the order of 10 to the power 13 Gauss, those are actually the neutron stars with very immense mass. Then the last possibility, that is the most fascinating thing for the entire like mankind, is the black hole. So if a star that started with mass that was greater than that was greater than around 18 to 20 solar mass, and after evolving through all the stages, the unfused core mass exceeds 3 solar masses, such type of star ends up, after the supernova, it becomes a black hole actually. And as it is like obviously very apparent, as the name suggests, black holes. So these appears to be completely black. No light is being emitted from these kinds of remnants, like as compared to white dwarfs and neutron stars, which are very hot, which emit bluish white light. Black holes do not emit any kind of light. Even light cannot escape the black holes, and they do not have a like specific geometric boundary, but we know, like we define something that is called the event horizon. And the size of such black holes is even very, very smaller than the neutron stars, of the order of few kilometers. I'm just talking about the stellar mass black holes, not the supermassive black holes, which is completely different thing. But the stellar mass black holes that we get as a result of the evolution of very massive stars that were originally at the top left corner of the HR diagram. So this is how a star which started as a molecular cloud, just the few molecules of hydrogen and helium, ends up and different types of products. Okay, so just a quick glance through the properties of each of these three phases. Okay, just bear with me for a few minutes. I have only three more slides, I guess, three or four. So the black holes. So these are formed due to the death of low mass stars. We generally classify the stars in categories: low mass, intermediate mass, and very high mass. So low mass stars die and gives a white dwarf in their wake. Here is an animation that is showing such thing. So eventually our sun, that the nearest star to us, like the life propellant on the earth will eventually die like this, and will be left in its wake. But we need not to worry right now, because it will take at least 5 billion more years to do so. And such kind of nebulas are usually observed around these white dwarfs. This is the material, or the material which was initially the part of this star's outer layers. Then the mass limit that I earlier mentioned, that the core should be less than 1.4, or like 3 by 2 of the solar mass, is actually given by the Indian origin scientist named Chandrasekhar, and that is why this limit is also called the Chandrasekhar limit. And this is basically based on the calculations that he performed, and found out that for any star's core which exceeds this limit, the white dwarf formation is not supported, and hence this limit, and even observationally, this was fortified. So hence the name was given, the Chandrasekhar mass limit. Beyond this limit, the star should form a neutron star or a black hole. Then the white dwarfs, like, actually happens after the white dwarf is formed is because they are very dense, very small. It is not actually possible to observe them or see the light coming from them because of the very small size. But what eventually will happen is the surface temperature of these stars will eventually go down, because there is no source of energy to replenish that amount of energy that is radiating as the light, and they will fade away into the universe, in the oblivion of universe, and will no longer be even uh, emitting the white light. And the material that will from these will eventually come handy in the formation of other on in the universe. Then the neutron stars. So okay, I will just have to, although I have already mentioned about the properties of the neutron star. So this is how the supernova of a neutron star actually looks like. And the remnant that is at the center is called the neutron star. So the neutron star is formed when the core mass exceeds the Chandrasekhar mass limit, that is of 1.4 solar masses, and the explosion that such kind of formation really gives away an energy of 10 to the power 6 joules, which is very lot of energy in terms of the observable energy that we actually use on the earth in our daily life. Then the extreme density is basically because it is comparable to the density of the atomic nucleus. The nucleus is very dense for any atom, and the density of these stars is almost comparable to the atomic nuclear density, and hence these are called the neutron stars. And the size is very small, and as I had already mentioned, the mass of such stars will be of the order of 1.4 or less than 3 solar masses. So you can expect, like, imagine it yourself that something slightly even heavier than our sun is being compressed to a size of just few tens of kilometers, just 10, 15, 12 to 20 kilometers. So how much dense object you will actually get at the end. Then the magnetic field and the rapid rotation of these stars. So as we all know that as our sun rotates, most of the stars also rotate. And while this uh, supernova collapse is actually happening, so due to the conservation of angular momentum, a very slowly rotating star will actually result in a rapidly rotating neutron star, and hence we observe these stars as rapidly rotating, or in more scientific terms, such type of rapidly rotating stars are also called the pulsars. If anybody has heard of these words, they will like relate. So rapidly rotating neutron stars are called the pulsars. And the magnetic field, again due to the like again a slightly scientific concept, due to the flux frozen and magnetic flux conservation, when a large size of object with some magnetic field is compressed to a smaller size, the magnetic field actually amplifies, and you get from 100 gauss of magnetic field, which is typical for a regular size star, you actually get 10 to the power 10 to 10 to the power 13 gauss objects. And okay, then the last, hopefully the last slide of today's talk, the black holes, the most fascinating objects that has baffled the human mind, is the end of a very massive star with the core which was greater than 3 solar masses, even after all the possible fusions that could have happened. And after that, no amount of fusion or anything could hold gravity, and gravity actually wins there, and the core is collapsed to a point of singularity where the density becomes almost infinite, and the material is, or the end product is so much gravitationally influencing that even the light cannot escape its influence, and we are left with some dark spherical objects in the sky that are called the black holes. Then we define something called the event horizon, beyond which no information can ever escape and reaches, we can be reached us, or if we cross that event horizon, the return is completely impossible, and that is what the event horizon. When the light beyond that event horizon cannot escape the gravitational influence of a black hole. That is why these appear to be black. And then again, the complete physics and all the possible phenomena that lead to the formation of such chaotic objects has been given by the general relativity predictions of Einstein. However, what actually exists inside a black hole will always, unfortunately, remain unsolved for the mankind, because no information can be transferred between the event horizon of a black hole. Okay, so that sums up my today's talk. I'll just conclude with, before this thanks slide, I have another uh, last slide that actually encompasses the complete loop of the stellar life. That is what stars form, the molecular clouds, they live through the main sequence and then they die. And then this cycle keeps on continuing and continuing, because at the end of the star's life, it actually emits that material away. And that material will again become the interstellar medium at some different time of, at different time in the universe. And that will again lead to the formation of stars, and the cycle will keep on continuing. And with each consecutive cycle, you will have the stars or the interstellar medium containing even heavier elements, material or the key ingredient. So the remnants create new stars, and some of the remnant is actually used up in the formation of planets. For example, if you see our solar system, uh, like the gas cloud from which our sun must have formed. When it ejected the material in the Tweety Tauri phase, the material that was surrounding it actually led to the formation of all the planets that exist in our solar system. So this is how the cycle keeps on going and going, and hence the stars drive the evolution of galaxies over billions or trillions of years. So the universe is constantly evolving through these stellar processes actually. That is why I termed these stars in the beginning as the cosmic engines. And then again, thank you for your patience. Now I can have any questions or any queries as any.
Yeah, thank you, Prince, for keeping the talk so simple and very like easy to understand. So
Yeah.
that is like really good. Yeah, you have made like so many concepts in a single talk, and they're like very easy to understand. So for the first time audience or like from the school level, so they can also easily understand it. So thanks
Yeah.
again. So now let us take a few questions from the audience. There are already few questions in the comment section. Let me read them out first, then I
Yeah.
will take questions from the audience directly.
I
So we
should
have a
stop
question
sharing, I
from,
guess. Can I stop sharing?
yeah, yeah, you can start sharing the
Oh,
screen. Yes,
oh, oh, oh.
yes, you can do.
Okay. No, 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 no. I accidentally clicked on the end call. Yeah.
Yeah, yeah. There is a question from Kamal Raj. So his question is, how different would the processes be when we start taking low metallicity into account, like population 2 and 3 stars?
Okay. So that is very, I guess, technical kind of a question. So see, the point
Yes.
is when we are talking about formation of stars, no matter what population type we're talking about, the presence of these heavier elements will always be just trace as compared to hydrogen and helium. So the process of formation
Mm,
of stars will not actually be hampered by the just fractional presence of these heavier elements. So stars will keep on forming in the
yeah.
same way the stars are forming or the type 1 population stars are forming, because these trace elements are not actually
Mm,
playing any significant role in that. The fusion
mm,
at the core will actually be happening for the hydrogen first, because the temperature you require to fuse heavier elements is supposedly heavy. But sorry, not heavy, the like higher. So
yeah.
like the role that the presence of these heavier elements play, I don't think is going to anyway change the path of the formation of these stars.
Yeah. I think Prince have answered your question, Kamal. The other question is from Anushka Das. How can we
Yeah.
determine the exact age of a star?
Okay, yeah, that's where your HR diagram comes in handy actually. So you
Exactly.
observe a star, you see its spectrum, from there you can determine its luminosity, its surface temperature, you plot it on the HR diagram, and that HR diagram, as I like actually I had to skip it because it is very very high scientific concept. So the axis, y-axis and x-axis are not only luminosity, you can like draw radius lines that like you can also estimate the time or the age of the stars from all those concepts. And then there is another like simpler method that we actually use for estimating the age of sun, that is we observe its actual luminosity, and from there
Yes.
we can calculate the like age of the stars using the concept of mass defect concept, that is how
Yes.
much
Yes.
amount of
Yes.
energy is being like released while the hydrogen is getting fused and converting into helium. So from mathematical aspect you can observe the
Yes.
luminosity, use this concept of mass defect, and expect estimate the life, or you can use the HR diagram for more precise estimation of stellar ages.
Yes. Right. Hope Prince have answered your question, Anushka. So we have one more question from Vikrant. Uh, his question is, if elements are formed before iron by atomic number, then how are heavier elements above iron like gold, iridium, platinum, so
Yeah.
and so formed on Earth?
Okay, so actually, I must have skipped that point while I was discussing the supernova. So what happens is, I was actually repeatedly emphasizing on the fact that only up till iron can be formed in the core of a star. So what happens is, when this supernova is actually happening, as I mentioned, a lot of energy is emitted or produced, 10 to the power 46 joules. So during that moment, this energy actually forces the iron nuclei to further fuse to form like even heavier elements, and within that instant of time, that same amount of temperature and energy forces the like synthesized elements to further fuse and form even more and more heavier elements. So it is at the instant of supernova, all the heavier elements beyond iron are actually formed.
Yes. Yeah. Thank you for answering the question. So then we have one more question from Sahil. Oh, okay. Sorry. Anushka, what is the difference in magnetar and pulsar?
Okay, yeah, it is basically the difference of classification. So for pulsars, we actually consider all those neutron stars which emit pulses either in the radio or the X-ray magnetic field of the order up to 10 to the power 12 Gauss. Those are classified as the pulsars. Magnetars are those neutron stars which have magnetic field that are 10 times more than these regular pulsars, that is 10 to the power 13 Gauss. Those are called the magnetars. And then there is this another definition that in radio pulsars, the emission is in radios. In X-ray pulsars, the emission is because of the accretion of material. In magnetars, neither there is radio, there is X-ray, but there is not a presence of any accretion material. Instead of that, these are actually producing pulses in X-rays. So for such systems, those are not in binary to get some accretion material, but still they are isolated individual neutron stars and still they are emitting in X-rays. Those are the magnetars.
Yeah. Right. Now Vikrant, you can unmute yourself and ask your question.
Sir,
Yeah.
Yes.
as our solar system was formed from a nebula, right? So
Yeah.
then,
Solar nebula.
Yeah.
so the remaining of the nebula should be there, right, in our solar system. But why is it not there?
Okay. So to answer this question, I'd like some help from Ravi to like mingle
Yeah.
the concept of radiation pressure that actually like throwed it away. And then the thing is, the point in the universe where our solar system was formed, we are not actually right there right now. So there is this
Yes.
tidal motion. Our entire solar system is revolving around the center of our galaxy. So all the remaining material that was ever there has been left somewhere else. Because not only because of our motion, but also because of the influence of close by, like what do we call them? Gargantua bodies or massive objects
Yes.
or celestial objects actually. So all that material must have been there if we had been lucky enough to observe our solar system just at the beginning of its formation. That must have been there. But
Yes.
since
Exactly.
such a long time has passed, so we are not able to see that material there.
Exactly.
Sir,
Yeah.
Yes.
is
You
the
can ask.
is the material shifting rare?
Uh,
Can you repeat again?
Is the material shifting rare?
I mean, can you be
no.
more specific?
Yes.
Like, for example, when the nebula was formed, the white dwarf is there, right? It got pulled away, right? So, like
Yeah.
that, is that thing happening rarely?
No, no, no. It actually is a matter of time, actually. So when I'm saying that
Exactly. Yeah.
after like explosion, a white dwarf is there and there is some nebula surrounding it. So we are technically observing that white dwarf system at very early stages just after its explosion happened. But if you take long enough, several billion, spend some few billions of years, you will observe that that nebula is no longer around that white dwarf. So that shifting is imminent. It just takes a lot of time for that to happen.
Okay, sir.
Yeah.
Thank you.
Can I
Yeah.
ask a question, sir?
Sure, sir. Yes, sir.
Uh,
Sure, sir. Please
Yes,
ask.
yes, sure.
Dr. Prince, I have a question.
Yes, sir.
I'm studying basically meteorites, and in
Okay.
meteorites, we have seen elements like iridium, or rather, iridium group of elements in the meteorites.
Mhm.
So, probably these have come from the asteroids, mostly from the asteroids. And the study which we are doing is primarily aimed at iridium group of elements. So, one of the indications of how the solar nebula has happened, or whether these are remnants coming out of solar nebula to the asteroidal belt, is also a very interesting topic. And I
Yes.
think the person called Yasa right now asked this question, whether do we have more belts between the sun and the maybe solar nebula?
Mhm.
Yeah,
Because
but yeah.
one of the reasons why I'm feeling is asteroid belts, then you have also Kuiper belt.
Yes. We have
And
Woods
beyond
cloud too.
Kuiper belt, if we have the solar nebula, and if an object from the solar nebula, as an asteroid or something, reaches the precinates of the Earth, one should be
Hmm.
able to see these elements also. And
Mhm.
one of
Yeah.
our studies, we have also published that what kind of iridium elements or group of iridium elements are possible. And in
Mhm.
that, we have also tried to look for carbonaceous meteorite.
Okay.
Okay.
And in the carbonaceous meteorite, we do find carbon, nitrogen, and oxygen also.
Yes, sir.
So, I'm sorry to, but I like the question by the younger person
Yes. He's
regarding
Vikrant.
how
He's Mr. Vikrant.
these elements happen. So
Yes.
it is just not up to carbon and iron. Beyond iron also heavier elements are formed. Now one
Yes.
of our ventures in our study is to look for transuranic elements
Mhm.
Okay.
for
Nice, sir.
meteorites.
So to
So
just to add on a point, there is some money, I mean, some interesting research that actually it is not one supernova which helped the solar system, I mean, formation of the solar system, but it was like two supernovae, and they have contributed to much of the heavier elements or denser elements we
Yes.
whatever we see on Earth and part of the solar system too. So it is like really interesting thing to know. And
Mm.
Mr. Jivaji also have added a point. He said like the remaining material from the solar system and solar nebula he meant is still surrounding us as a Woods cloud and is source for many comets. So it's some interesting point to add on. So yeah, it is not just one supernova, but two supernovae which contributed in the formation of these elements actually. So yeah,
Yeah, I guess that also
and
explains because Sun is a type 1 star, so we can expect that also.
yes. Exactly. And we have few more questions. And one question is from Krishnan Kutti. Is redshift a factor in the HR diagram, like the distance of the astronomical object? Can you please brief on the concept of redshift?
Okay, so redshift is basically something that you will observe when an object is moving relative with us or the observer. If it is coming towards us, we will observe blue shift. If it is like proceeding away or exceeding away from us, we will see something red shifted. So that is the general concept of redshift. But if you are talking about the gravitational redshift, then I'm not sure, because that thing is not incorporated, I guess, in the HR diagram. And also, I
Yes.
think redshift and blue shift, we actually account for these shifts while we are generating these HR plots, because we actually talk about the absolute magnitudes and absolute luminosities when we are plotting the
Exactly.
stars on the HR diagram. So those red shifts and blue shifts are taken care of beforehand.
Yes.
Clear?
Yes.
Yes.
Yeah.
You have question
Uh,
again? Yes.
so you have one more question. Vikrant, you can ask.
Sir,
Yes.
Yes, yes, you can ask.
basically, many people get confused between the HR diagram, M-type stars, and the redshift, as they're both red, but the red color in M-type stars is due to the s- spectrum, and
Yeah.
red, redshift is due to the extent of the spectrum due to universal movement.
Yes. That is a very,
Thank
very
you for
good point
adding that
raised by.
point.
Yeah. The colors that
Anushka,
are
you can
there on
ask
the
your
HR
question directly.
diagram, those are the absolute colors due to the surface
Exactly.
temperatures, not because of the shift,
Uh,
like motion.
Anushka, you can
Okay.
ask your question by unmuting yourself, or you want me to ask that question?
I think I read her question, that how we are formed
Okay.
of step.
Acha,
Yeah,
okay,
that,
yeah.
that was the question. Okay,
How are we all
because
made of
we,
stardust?
yeah, so as I already mentioned in the beginning, the entire universe has abundance of hydrogen and helium. Although our human body is made up of all the other elements as well. And where do these elements came from? Is from the death of the very early primordial stars that were purely formed of hydrogen and helium. So that is why we call it that we are made up of stardust, or the ashes of the dust. The elements that we today have on Earth or in our solar system, in our bodies, actually came from the death of some stars that were there billions of years ago.
Yeah. Any more questions? You can unmute yourself and ask questions. If not, we will end the session. If you have any questions, you can ask. Or if I have missed
I
any
guess
question, please let me know. I can ask that question for you.
you can write to me if someone is interested in asking a
Yeah,
question. You can
exactly.
contact me.
Yeah, yeah. You can find Prince on LinkedIn also. If you have any questions, you can ping him on LinkedIn, or you can write to him. If you have any questions, or you can ping to me also. I can share those questions with Prince. So at any given. So I think you know, I mean, none of have any like questions. Yeah, I think we can end this session. So thank you once again, Prince, for giving us time.
Yeah, yeah,
So
sure.
you made the presentation very, yeah, very like neat and clean with so many graphics, which help them
Yeah,
to
that,
understand it easily. Thanks for keeping it very simple and straight. And you have covered so many concepts actually. You have covered the whole stellar formation and evolution
which is very
in very
difficult, I guess. Yeah,
exactly. For common audience, it is very difficult
e-
because
exactly.
sometimes even we face some issue while explaining some parts of it. But you made it
Yeah,
like you
so
kept it like very simple and straightforward. Yeah,
that
thanks for
comes
doing
from
that.
practice actually. Yeah, I'd like to share this thing, because that I have presented here, it took me one complete year during my first year of PhD to go through the entire thing that I have presented today. So it is very difficult to
So
like
your
compile each and
pre-PhD
everything
exam, I
within.
guess.
Yeah. Yeah. Okay, so I guess we have another
That is what
question.
we learned during PhD.
Yes.
Uh, yeah, Vikrant, you have any question or you want to add something?
So there I have a question
Yes, please.
Yes.
and also like a add-on.
Okay, please do.
Like as yesterday I was like researching about black holes by my own,
Okay,
Mhm.
like
yeah.
in a physics book, and then I discovered like gravitational waves, like ripples of space time,
Yes.
Yes.
and then also gravitational waves can also stop time, it seems, and we don't even notice.
Sorry, I didn't get the last
Okay.
part.
No, what he read was whenever when he came, I mean, reading about gravitational waves, he came
Uh-huh.
across that these gravitational waves can stop time, and we don't even know
Okay.
about it.
Okay.
And
So
sir,
eventually, yeah. Uh-huh.
and sir, while also reading about black holes, like I thought of antimatter, and in antimatter, I might think that the anti-neutron might exist.
Nice.
Yeah, that is good
That's
It's a
it.
reading,
bit
I
weird,
guess,
actually.
for his age. He has been reading way too
Exactly.
beyond.
He's Yeah, yeah. Actually, he's like very enthusiastic kid. So he attended my
Yeah.
astronomy course when I was
Yeah,
working
I
in
remember.
Birla. He's like very
Even I remember
passionate.
him from
Yeah,
the previous talk also. He was there. I was also there in the previous talk in
yeah,
which
yeah,
my
yeah.
students also
Yeah.
joined.
You were in that session, I guess. Yes. And to
Hmm.
add on to Vikrant's point, like gravitational waves do stop time. It's not exactly like they do not stop time. They may cause very slight changes in the fabric space-time. Okay. So how we experience time locally, it may like alter it. I mean, slight
Hmm.
changes may be brought, but it won't stop it exactly. Okay. So I don't know like where you have referred it, but yeah, the word do not, I mean, this stop is like not appropriate maybe for now. So it's better if
Ah,
we call it as like a slight change in the fabric space time, which can be experienced
hmm.
locally, especially. Yeah. So
Okay, sir, and this is the reason why they add extra seconds almost every decade,
yeah.
sir.
So
Like
you
in,
can say
two,
slight changes, yes.
like in 2005,
Mm.
1 second before the new year,
Mm-hmm.
2006, they added an extra second to equalize the time again.
Nice. Right. Thank you so much for adding that point, Vikrant. So keep learning
Yes.
like that.
It
Explore,
it was
expand your
something
horizon.
new for me also. I also learned something new today.
Yeah,
Thank
he
you,
keeps on
sir.
adding very good points. Whenever he reads something,
Yes.
he is interested in sharing that with us. That's really good.
Yeah.
Yeah, thanks for
I guess.
everyone. Thanks for each and every participant who participated and engaged. So we will be hosting few more talks. And if you have any questions, you can ping us. And I will be sharing this video on YouTube also. You can write comment in if you have any questions, you can write in the comment section so I can share it with Dr. Prince. He will be answering few of them. So have a great night. Thank you once again for everyone, and especially thanks to Dr. Prince for giving
Yeah,
us
yeah,
time.
sure. Yeah,
Yeah,
I
yeah.
actually this was my first time addressing general audience, so I guess I
Oh,
hope
that's
it
nice.
was, yeah, more productive. So if
Yes,
it
it
is a
was.
success, then uh, you can invite me again, and I'll deliver some
Sure,
other
sure, always.
interesting talk
It is
also.
like
Yeah.
it is like really good actually because you are like you are not like very fast. It is like very cool and calm. So you tried
Yes.
really great actually. You made it like kept it
Okay.
very simple actually. Sometimes even we try a lot to keep it very simple, but we may not.
Yeah.
But you kept it like very
Even.
simple. You have covered a whole deep subject in a simple talk. That's really nice of
Yeah.
you. Yeah, we will be having
Okay. Thank you
many
very
more such
much.
sessions. Yeah, many more such sessions in near future. So thanks everyone. Have a great night. Take
Okay.
care.
Thank you, Kamal Raj, for the praise.
Yeah.
Okay. Okay.
Some of them are asking your LinkedIn. I think we can share
Okay.
your LinkedIn link with them. So I will
Okay.
be
Right
doing
now.
that on our
Yeah.
official
Okay.
page.
Okay. Sure.
Yeah. Yes.
Okay. Thank you,
I do
everyone.
share. You can follow our website. I do share Prince LinkedIn with you. Don't worry. Yeah. Please take care, everyone. Good night.
Yeah. Good night and bye.